Okay. So this class will be video recorded. What that means is that if you happen to miss a class for whatever reason, you can probably get something out of the videos. It might not quite be Oscar-winning quality, but it'll be good enough such that you can make some sense out of it. There'll be a better camera from next week on. Second question, can everybody in the back hear me?
Can you speak a bit louder, please?
No, not really. This is already loud. So we are finding a microphone. Eventually it'll show up, and so probably within 10-15 minutes you'll be able to hear me a bit better. But if I speak louder, then towards the end of the class nobody will be able to hear me because my voice will be small. Sorry about that. So we're fixing this. So as said, this is the first class that both Barnabas and I are teaching. What this means is, if you have questions, concerns, anything of that kind, you should let us know. Now, there's a couple of things you should do if you are signed up for this class or waitlisted. First of all, go to the class homepage. Read the stuff that's on that page. We're going to go over the main parts of it today as well, but this is really the place that has the definite answers for everything, at least for that class. Secondly, you should sign up for the Google group for the class. This is where you should ask questions unless it's something super embarrassing that you only want to ask any of the TAs or me or Barnabas in person. If it's something that you think somebody else might benefit from, you should ask it in that group. Almost certainly somebody else will have had a similar question. The other thing is, if you have a question before posting it, check whether or not somebody else has already asked it. It's the usual RTF thing. Okay, now I have a team of 5 highly skilled TAs who've been around at CMU for longer than I have. They're sitting here in front. So it's Leila, it's Ina, who's I think at the moment just getting the microphone, Jiti, Junior, and Moo. And so if you could all stand up, please, and of course also Barnabas, such that everybody else knows who they are. They'll be handling the recitations, they are handling the grading, they will be probably writing some of the assignments both for the exams and also, for, your standard homework. So it's a good thing to know who they are. My guess is they'll now very soon disappear because I hope they know enough about machine learning not to really need this class to learn about it. But they might be here occasionally also to find out what Barnabas and I are talking about in class. Okay, so thanks very much for having that team. And guys, if you want to do something else more useful now, just leave it anytime you want. So let's actually start with some important administrative stuff. So the first thing is, as if you haven't already noticed that the lectures on Monday and Wednesday, 12 to 1:20, we'll probably have like a 5-minute break sometime in the middle. But other than that, it'll be pretty much 80 minutes of machine learning. The other thing is the recitation is Tuesday 5 to 6. And there's a slightly different lecture hall this time, as in next week, as opposed to for the rest of the class. That's just because we only got one room for most of the time and another room for once. Fine. Office hours, mine are Tuesdays from 2 to 4. Barnabas's are TBA, probably Thursday. Now, in terms of how you get evaluated for the class, we're trying something a little bit unusual. So the thing was that we figured, well, basically having project, midterm, homework, and final, so all those 4 things is a bit of a drag, right? So it's a lot of work. So we thought, okay, how can we make life a little bit easier? Well, you can skip one of those 4. Or rather, well, you get graded for all 4 if you do all of them, and we count the best 3 or 4. So if you screw up on your midterm, it's okay. If you screw up on your homework, it's okay. If you screw up on both, well, it's not so good. The only thing is, finals are mandatory. If you're auditing the class, you either need to do both exams, or you need to do the homework and get 50% in each case. right? So you can skip the entire class and just do both exams. The reason for not only making the final mandatory for auditing is because we might not cover all the content in the final. We might cover primarily the first part and the midterm, obviously, and not cover so much of that in the final. Okay, final counts 34%, just to make it sum up to 100. Now with the homework, there'll be 5 homeworks, and the best 4 out of 5 count. So same idea as before. This is just to make it easier rather than having the poor TAs keep track of how many days late each of you has been for any one of his homeworks and, you know, waiting until some late homework submissions come in or God knows whatever. It's basically you submit your homework on the due date or before, so you can email in the homework, and there'll be an email address for submitting homework electronically. So nobody prevents you from, well, submitting your homework from, say, Australia, as long as you have an internet connection. But if you're late by the due date, well, it doesn't count. On the other hand, it's the best 4 out of 5, so you can screw up once and it's still okay. So what this does is, I think, should give you enough leeway in case you can't make it for whatever reason once. But it also, of course, gives those who do all 5 homeworks a slight benefit. So it also means if you only manage to get half of it done, still submit it. It's probably a better idea. Okay, so the Google group is there. I'm not assuming you'll be able to immediately remember all of this, but if you go to the class homepage, you'll find all the things there. So go to my homepage, alexsmuller.org, and there's a link to the class. So this is then, yeah, the homepage will also contain videos, or let's say rather links to the videos which will be up on YouTube. This might take 1 to 2 days, simply because it'll take us a while to actually upload 4 to 5 gigabytes of video, and secondly, it'll probably take Google a couple of hours, maybe a day, until YouTube processes these videos, because they are not quite as high priority videos as, let's say, a music video. So therefore, it might take a day or so until it's available in high definition, but we hope that within 2 days after class, you will have the video available. Okay. Most likely, also the recitations will be recorded, so in case you miss out on something, at least you can do so. The next thing is ask questions at any time. So if you have any questions right now, ask. Any questions? Everything clear? Okay, awesome. Projects and homework. So, I mean, don't copy. I mean, you know, you're wasting your time otherwise. I mean, you're not going to learn anything. I mean, there's no way we can perfectly check that you didn't copy from anybody else, given that it's probably 130, 140 homeworks. However, if we find it, well, you just get no points on that. However, teamwork's okay. You should, you know, discuss and so on, but if you just, you know, photocopy the assignment and just submit it, then we're going to be less than happy. For projects, 3 is a good number. 2 to 4 are okay, so look around, you decide who you want to work with. If you have more people, you will be expected to deliver a little bit more, and the other thing is we're not going to try and distinguish who did what in a project. You all get the same score. So in other words, if you're the only really hard-working guy and you team up with 3 guys who do absolutely nothing, well, okay, life sucks. So basically, find better team members. That's the only thing I can tell you in this context. Start those projects early if you want to do them. There'll be 2 deadlines. One is for a project proposal. This way we have you in the system and we know what you're doing. And then there's a midterm presentation which is going to be due 2 days after the midterm exam, and that's just 1 page which says, by the way, this is what we're really doing, and here's what we've accomplished so far. This is just to make sure you don't forget about the fact that you actually had a project. And then in the end, well, some report is due. There are more details on exactly, you know, style formats and so on, and how to do it on the homepage. So here's a bar. So the Stanford machine learning course did, I think, a fabulous job on their projects. Let's see whether we can at least match it or maybe even beat it. Hey, who said CMU would be less talented than Stanford, right? So this would be something to aim for. Color coding. Green stuff is really important, so that's why those slides here were all green. Yellow stuff is, yeah, it's pretty good that you know. Red is regular stuff. Well, you know, you should at least remember that we talked about it at some point. So, feedback, please. Let us know. And letting us know means you can post that feedback on Google Groups. There'll be somebody from the TA team who will, you know, look through the groups at least once a day and find out if anything is going wrong. Or also if you have suggestions of something that, let's say we covered something and it wasn't quite so clear, and if there are a bunch of those questions, well, we can infer from that, you know, maybe we didn't explain it so well, and, you know, we'll go through it again. So it's our first class at CMU, and we want it to be useful for you. So therefore, it's important that I know what you know. And since this is, as far as I can tell, essentially a class of people who've not done machine learning as their PhD, but basically it's a mandatory class and you need it maybe, maybe not for your work, it's really useful that we know what you've learned in the past. So for instance, we are assuming that you know linear algebra, that you know optimization, that you know basic probability. However, to make sure that this is not just an assumption, the TAs will actually cover some of those things again in the recitations. And they'll figure out in a couple of other ingenious ways what you know. So, let us know if something's not clear. Also, if I'm teaching or Bandabash is teaching and we explain some stuff and we don't explain it very well, do ask. So this class seems to have a fixed schedule in the sense that, well, we've basically, you know, planned out all the lectures. That doesn't mean that we absolutely have to follow that schedule. There are a couple of lectures in there which we can skip and go through other things in more detail. Let us know if you have questions. Okay. So this is basically the basic administrative stuff. So let's actually get on to machine learning. So what are we going to do? Well, we'll obviously cover, you know, the basics, just, you know, what machine learning is, what the basic statistical parts are, you know, what you could use it for, and, well, it's kind of hard to really precisely define machine learning. I mean, going by the definition of pornography from the Supreme Court, as in we know it when we see it, I think this is probably the most accurate description of machine learning. Some of the things that you know we'll need is, you know, some basic algorithms like naive Bayes, nearest neighbors, decision trees, neural networks, perceptrons. You should be able to, you know, at least relate to that and remember, there was this class where we taught this. Then we'll touch upon a fair number of, you know, kernel-related methods. I call them generalized linear models, so support vector machines, regression, novelty detection, kernel PCA. We'll cover some theoretical tools, risk minimization, convergence bounds, a bit of information theory, so at least afterwards you'll know what entropy and mutual information are. We'll do a fair amount of graphical models, so exponential families, graphical models, dynamic programming, explain a little bit what latent variables are, variational and sampling techniques, and then we'll discuss a few slightly different situations where basically you have interaction with the environment. In other words, you know, online learning, or you're dealing with bandits, as in one-armed bandits type settings, or reinforcement learning directly. And time permitting, I'll cover a bit of scalability in the end, on how you can scale some of those algorithms up to, let's say, Google or Yahoo sizes. So the hope is that what you'll get out of it is, you know, stuff that you would need for a startup. Almost certainly, if you get this class here, you will be way better than the average machine learner data analyst at the average Silicon Valley startup. And I'm speaking from experience here. I hope that it'll be useful for your PhD. If you just want to make money, well, it should help you getting a job at Wall Street, or, you know, conserve the environment, or maybe cure people. It's your choice what you want, right? But basically, I hope that this class will be useful for you. So, if there are any specific things that you're not sure of, let us know. Post it as, a wish list of things I wish we covered such and such on groups. And if enough people ask for it, well, we might do it. No, we're not going to cover genetic algorithms, and we're not going to cover fuzzy logic. Sorry. But for the rest, I'm fairly open. Okay. Now, what is machine learning? Let me show you a couple of examples. And so, these are two examples of collaborative filtering. In the first case, it's probably collaborative filtering gone wrong. In the second case, it works reasonably well. So what do we have here? Well, these are some books that Amazon is trying to recommend me. It was a couple of months ago, and as a matter of fact, I have those two books on my shelf, and I was even thinking of getting that one. In other words, that's, machine learning, because basically, based on your previous purchase history of books and other things, it tries to recommend you additional books. Well, which is kind of awesome. Now, here's what happens if you go and have several people using the same Netflix account, you get garbage. This is a movie I watched. I don't think I would want to watch any of those four. That's basically just if, you have children's movies, and then my wife watched some movies, and I watched some, and it was kind of the least common denominator, which wasn't very good. So, but in general, collaborative filtering is a really useful application. So for instance, if you go to LinkedIn, Yahoo, Google, Facebook, and you look at your newsfeed, the content that you're seeing there is usually adjusted in one way or another based on your past preferences. This may not be very obvious, this may be a very gentle personalization, but it definitely does happen. So here's another example, and I guess you're probably too young to have played this game. It's black and white. So the idea there was you play God and you have an avatar, and the avatar is supposed to learn based on your actions, what you're doing. In this case, the avatar is, one giant cow. Okay, fine. Now what happens is actually, this was, to my knowledge, the first serious major implementation of machine learning in games. Basically, they built the perceptron, and based on you could be good or evil, and the cow or monkey or whatever other beast would then also mimic yours, and you could train a really vicious cow out of that. But the problem is they built a perceptron, and initially it worked very well, and towards the end it actually stopped working very well. And basically, this is because they didn't understand machine learning well enough, and they didn't understand capacity control, model selection, and regularization. So that is actually pretty much what killed the game. It was a very nice idea, but in the end, the fact that the guy who implemented this machine algorithm didn't quite understand machine learning well enough, I think pretty much cost them half the revenue. I don't know whether you have an Xbox at home and you play Forza, and I don't have one, but a friend of mine built this system, Rolf Ebrich. So basically the idea is, you race around in this racing game, and essentially the system will learn how you drive, and then you can get an avatar. In this case, they call it a drive-atar. So you can patent it and market it, and you can race drive-atars against each other. So these are models that are essentially trained based on your competence or maybe lack thereof in driving. It's another example of machine learning. Or also the true skill system, where I guess if you want to play in a first-person shooter and you team up with some buddies and you maybe don't know all of them, but at least you want to make sure that they are equally good or bad at shooting up others, and that the other team that you're playing against isn't way better or way worse, because otherwise it's not so much fun. Here's something that you might have used today. So it's a picture of my mailbox recently, and here's some ham, here's some spam, and basically, it does a fairly good job. So for instance, there are all those spam conferences, and it automatically finds out that they are spam conferences. And this stuff is more or less hammy. So this automatically classifies a lot of incoming email based on what I've clicked on in the past, and also what other people think in terms of ham and spam. So you could even think about what's the opposite of spam in the context of email. Well, that's basically the really, really important emails, And as a matter of fact, that's the priority inbox here. So this is basically anti-spam to the very extreme. So this is currently in production at Google. Here's another example. So these are another website. This was basically running on Yahoo. And essentially what it was doing is it was logging over a period of about 1 or 2 months the user's activity. So looking at what they query, which web pages they click on and all that. And based on that, it would automatically determine what the interests of a user are. And this is all automatically generated, so there is no manual interaction whatsoever in it. But it still tells a fairly nice story. First of all, you get fairly nice, topics of interest, like, the only manual thing is the naming, but if you have women, men, dating, singles, personal, seeking a match, dating, I think, is a pretty good name, and so on and so on. And so these are 2 users over 40 days, and so you can see this guy, let's say it's a guy, is heavily interested in dating, and maybe a bit of an airhead. At some point, well, he's, oh, that's awesome, nice. Yes? Awesome. Okay. Can you hear me in the back now? Okay. So anyway, so after about a week or so, this guy, starts worrying about his health. Maybe somebody told him he's too fat, or maybe something else went wrong. And, okay, his interest in dating takes a bit of a dive. Then he discovers baseball, and he's even less interested in dating, right? And you can make your own story out of that. Or this person here, first hardcore baseball fan, let's say another guy. We don't know the gender or anything else about that person. That would be very kosher if we did. But then after a week starts worrying about finance, and then another week and a half later starts applying for jobs. And it goes basically just baseball takes a dive. So this is stuff you can get automatically, which is something between awesome and creepy. So why would you care? Well, first of all, this way we can figure out which content you might actually like. Secondly, these are the times when, oh yeah, by the way, here's some tickets for baseball. Or yeah, here's some unsound financial investment. And by the way, here's a job site where you might want to post your CVs on, right? So these are cases where it makes sense to then, take commercially useful actions. Or, recommend some other content. So this is why machine learning in that context is actually quite useful. And you don't want to train somebody about, what those topics might mean in some other random language we may not even have anyone speaking it in the team. Another thing that you might have encountered is basically check reading. So obviously you won't be seeing any checks of mine here, but basically if you go to an ATM or you use your mobile phone app, you can basically snap a picture of a check and it gets uploaded and then put in your account. And at some point you either need a lot of humans typing that in, and that would be kind of miserable, or alternatively you have some algorithms which do this. And that's actually been around since basically around maybe the end of the 90s. Except that by now it's actually very widespread. Another cool example. So this is from Andrew Ng's group, the autonomous helicopter. And so if you look at this, I think it looks pretty awesome. This is all learned, so this is deliberate behavior. And you can see now it's in perfect control again. There are less spectacular movements as well, but basically if you go to that site here, you'll see a lot more of those videos. So what they did is they basically had some helicopter, model pilots, fly those things, and they would then, learn a controller for it, and then they were able to essentially replicate this. So it's similar to the driver tires that I showed you before. And they were basically able to, get any maneuver working that you could wish for, which is really awesome.
Sorry,
Yep.
question about that. What stops me from just
mimicking entirely what helicopter pilots do?
Well, you might actually want to combine various sequences. The helicopters change a little bit over time, so you might have a gust of wind or something, so the same control inputs might not always be really appropriate. By the way, this is an awesome question. So basically, why can't we just play back exactly the control inputs? Because, well, the environment, the helicopter, other details change slightly over time, so therefore just playing back the original inputs doesn't quite help. So, but by the way, awesome questions. Keep on asking those. This is good. Any more questions? The other thing is simply you might not have them in the same initial conditions when you enter that maneuver. So there's a lot of reasons why this is less than trivial. This image layout, so what you probably cannot see is the very details, but these were like a couple of hundred photos taken with 2 different cameras, different resolution and all, over a period of maybe about a week. So this was a vacation that we had before leaving Australia. And the idea was, how can we lay out the images in such a way that, similar images are close. And then it actually turns out by maximizing dependence between a grid and the images themselves, you get a fairly efficient layout. And so this gives you a good image browser. That would be more along the unsupervised algorithms. Another example, so there's actually a lot more going on behind the scenes. If you search for mesothelioma, which happens to be one of the most expensive ads that you can run and click on, so basically, in other words, if you really hate those mesothelioma lawyers, well, search for this stuff, click on it, and they'll pay a very substantial amount of money. No, don't do that. Otherwise, it's bad. But yeah, basically, yeah. It's actually quite interesting that different countries have very different top-paying ads. So basically, if you click on an ad and sign up for stuff, then they pay, in this case, Google or Bing or Yahoo or whoever else, some money for that click or that conversion. But to figure out that these ads should be shown there and which ones should be shown, that's then essentially up to the machine learning algorithm. And a fair part of the team that does this work actually sits in the Google Pittsburgh lab just up the road from here. Here's another story. So this is actually something that happened to a startup, and I cannot tell you which company was that bought them in the end, but you can probably figure it out from where I worked. So some startup builds an ad exchange on web pages. So basically, the thing is you have a web page, you want to show some ads. So you go and say, well, here's my web page, find me good ads. And you register there, and you have an API call that you can the ads on and God knows whatever. And then the clients bid on some opportunities, and this market takes a cut. And the system got really popular, and well, so then they found out in this ad exchange that stuff worked really better if you had a reasonable match between maybe the pages and the content and maybe the users. So the programmers added a couple of if-then-else clauses, like if the same word occurs, hey, this is good. And then they realized, hey, this is giving us money, so let's spend some more time, and they added more and more and more clauses. And then at some point, this programmer had an epiphany and said, hey, this looks like a decision tree. So he had never learned much about machine learning before. But then at some point he found an article which described decision trees and said, yeah, that's exactly what I'm doing. And so they downloaded the decision tree package and ran it, and it worked better. And they made more money. And then, well, at that point they were interested in, machine learning. They heard about decision trees, then they heard about boosting, and they added boosted decision trees. And by that point, 2 things happened. First of all, they had a pretty well working system. Secondly, pretty much the entire infrastructure was for decision trees, or boosted decision trees, which made it then a little bit less fun after that startup was bought to, essentially retrofit a slightly more advanced machine learning algorithm to it. But this is an example where, that guy did really well for himself, through that and also helped the company very much. But this is still a very common scenario where people don't understand initially that something is actually a machine learning problem. So they just go and, write a couple of lines of code to, be smart about the data. And that smarts gets them somewhere, but actually they could get much further if they really realize that machine learning is probably a useful tool there. So this gets me to the end of that first part, namely, programming with data. So what we really want is we want to have robust fault-tolerant systems that can actually easily adapt to whatever problems I have at hand. So this is why I'm calling it programming with data, where rather than having some rule-based implementation that can be difficult or brittle and is really a pain to implement and sometimes doesn't really work so well, I just show the system examples like if X is observed then I want Y to happen. And I show it a lot of those examples. And I want my machine learning system to take those examples and essentially generate a piece of code which will do Y if X happens, or at least if something similar to X happens. And this is what I hope you will be able to do at the end of this class. As a matter of fact, I'll show you the very first few algorithms today, and then Barnabas will show you some more on Wednesday, and the algorithms will just get fancier over time. But we hope that you'll be able reasonably soon to start by building those algorithms and deploying them. And this will also help you with your project. It will also help you, I hope, with your research. Now, one of the distinctions is already between supervised and unsupervised. For supervised, basically, you have a question and you have a desired answer. For unsupervised, the first thing you need to do usually is to even start asking the question. And I'll get into this into a lot more detail now. But before that, do you have any questions so far? No questions? Wow. Okay. So, whenever you see this Etch-a-Sketch, you can forget about anything I said before. Well, for at least it's a new unit, so if you got lost up at this point, you can pick up again. Let's talk about a few problem prototypes. So the first thing is supervised learning, and the simplest thing you can do in this case is binary classification. So in binary classification, so essentially this y is going to be a 1 or a minus 1. And so given x, we want to find, a 1 or a minus 1. So for instance, spam filtering is something of that kind. But sometimes you don't only have two categories, but you have multi-categories, right? So let's say you go to a web page and you want to detect what the language of the web page is. Well, that's kind of useful. So for instance, if you're using Chrome, it's reasonably smart in detecting, this web page is, let's say, in French. Would you like me to fire up Google Translate to translate it into English? Right. So for that, it needs to be smart enough to reliably detect what the language of the page is, which it usually gets right, except that occasionally mistakes Google Drive for Albanian, but usually gets it right. So that's a multi-class classifier. And while that may be very obvious for French and Spanish, there are a whole bunch of languages where I would have a lot more trouble figuring out exactly what language it is. You might want to do regression. So, for instance, given x, find y. So, let's say you want to find out, what tomorrow's stock value is. As a matter of fact, that's actually more prediction, but, maybe you want to find out how much to charge a particular user for a particular item on a dynamic, pricing engine like on Amazon. Or you have an entire sequence and you want to annotate, let's say you want to find the genes in that sequence, you want to find the start and stop codons, or you want to identify the named entities, you might want to identify how various words relate to each other, or for instance you have an audio signal. As a matter of fact, you're doing that right now. Because what you're, I hope, are doing is you're listening to what I'm saying, and then your brain is annotating that sound sequence, re-annotating it with what you think that I might have said, right? And then I hope you actually remember some of those. But at least if you're listening to me, your brain is currently doing sequence annotation. You might have hierarchical categorization. So in that case, you have an entire tree of objects. I'll go through all those things in a bit more detail. And the last, well, I mean, there are a lot more problems of that kind where you want to get y given f of x, but another really important one is prediction, where, let's say, today's value of various securities in the stock market, well, we want to infer what tomorrow's securities will be worth. So this is a bit different from just a simple regression problem, because you can't really look ahead.
Well, I was going to ask, doesn't prediction include all the other categories in some sense?
Well, you could do prediction for any of those. That's true. What I wanted to explain is that the setting is a little bit different there, where you basically only have the observations until now, and then you want to, predict for the next step. So in this case, the difference is less whether it's a classification or regression problem, but more that you have data up to that point, and then you want to do something at the next point. The other thing is that, it's fair game to use all the previous labels that you had for the next one. So for instance, if you want to forecast the weather for tomorrow, it's a pretty good indication, at least, let's say in California or in the desert, to use today's weather. Well, yesterday's weather in Pittsburgh wouldn't have been very good for today, but usually the constant predictor is not too bad for a weather forecast. So let's go into a little bit more detail. Let's say this is binary classification into ham and spam. And so here, this is actually a support vector classifier, and there are some, red and blue dots. Let's say this is ham and this is spam. And so it tries to find a function here, which is, very positive here and very negative there. Okay, and then you just take the sign of it, and, whenever, the sign is positive, you say it's ham. Whenever it's negative, you say it's spam. But there are lots of other classifiers that you could build, but that's the granddaddy of all, machine learning problems in a way. The reason why we study those things is because, first of all, this is at least some commonly agreed language for which a lot of people have implemented code. Secondly, in many cases, whatever problem that specifically you're interested in can be reduced or transformed into one of those basic problems. So that's why it's really important for you to remember at least the names of those problems and roughly what they do, much more than the specific methods, such that if you encounter a similar problem in practice, you know which terms to search for, such that you actually will find the right algorithm. I'm under no illusions that you will remember all the algorithms of the entire class. That would be awesome if you did, but even if you don't, at least I want you to be able to remember which questions to ask and which terms to Google for. Yep?
Then why is there no technology on the exams?
Why is there no what?
Technology on the exams.
No technology on the exams. Well, basically, because otherwise you could really wing it. So otherwise you could download all the slides, but yeah, that's a good question. So, thanks for going to the class homepage in the meantime. Basically, I want to make it reasonably fair, such that not the people with the fastest internet connection and the best skills at Googling can actually solve something. The other thing is, you need to remember something. And if you remember the algorithms and the names of the algorithms at the exams time, then maybe in a year's time, you will still remember the names. But if you only vaguely remember the names now, you will not even remember the problem settings in a year's time. So I think it's just a little bit more fair if it's an exam where you just have pen and paper and you think. But for all the homeworks and so on, of course, you can do everything else. Multi-class, well, the simplest example, I guess, where people actually work a lot is, optical character recognition. So here there are 10 different digits, and you want to find out that this is a 7 and this is a 1 and so on and so on. So this was actually one of the first applications of machine learning at large scale, basically to sort mail. Because it's just an incredibly tedious and awkward and boring task to take all the letters and punch in the zip codes. So what you needed is an algorithm to identify where the zip code is located, then to segment it into individual digits, and then to recognize it, such that users, well, as in postal workers, only had to process a very small number of them. So this was still a big deal, let's say in the early 90s. So, for instance, the US Postal Service actually created competitions on that very issue. So think of it like Netflix, but just anno 1995. And that really, pushed the state of the art forward. Here's another example, well, regression. So let's say you might have, some, want to estimate the size of the peak of some bird, and okay, well, you can try to regress on it, or here's something on the basically, for instance, Ohm did one of the first regressions. It's called linear regression for Ohm's law. He assumed no offset, and he realized that actually a linear fit is pretty good, and that the regression coefficient is then what he called the resistance. Right? Here's something slightly more recent. Let's say I have some gene sequence, and I want to annotate it into, well, all those fancy, colorful markers here, which probably mean more to a lot of you than they mean to me. But basically, for a given sequence, you want to annotate it in a meaningful way. As in, let's do speech recognition, you want to segment activities. Let's say I run around with my cell phone, and the cell phone wants to find out whether I'm walking or driving or cycling. Well, why is that useful? Because, for instance, if I'm running, then maybe it needs to ring a little bit louder before I hear it. Or I might want to identify identities in the text. So in all of those cases, you actually have an entire sequence. So it matters where the position of various symbols is, and it's only really the relation of those symbols that helps. Here's another example. This is a little bit stale by now. DMOS, I think it has something in the order of, well, it has 100,000 editors, 1 million categories, and 5 million sites. That should already tell you something about that something is awfully wrong about DMOS, right? Because if you have 5 million sites and 1 million categories, it means that a lot of categories have maybe just one entry. Nonetheless, the first 2-3 levels of DMOS are probably not quite that horrible. And if you had a mechanism of automatically taking web pages and putting them into these categories, it would be quite good. This is, by the way, considered a small problem by internet standards. So the public web page crawl that you can get on Amazon for free has about 6 billion pages. So 3 orders of magnitude larger than this. Here's a small snippet from the gene Ontology directed acyclic graph. So you don't only have a tree, but you can have arcs going either way, so they can merge again. It's called sometimes also the GODAG. And so what you want to find out is what on earth is a particular gene doing, and so you want to be able to map genes to any of those boxes. Now prediction, there's a couple of internet companies, over about a year, and so you can see how their price developed over time, and actually most of them did fairly well. And well, just doing a regression here, knowing the left and the right hand side is kind of lame, because you want to really know how does this curve continue into the future. And that's basically where prediction comes in. So, any questions so far about supervised learning? Yep.
So if an instance has multiple labels, what kind of learning is that?
Good question. So that depends a little bit on what the structure between the labels is. So in some cases, so an example of this would be, for instance, if I have several languages on a web page. That can happen. You can build classifiers, estimators specifically for that. I would probably search for classification with multiple labels, and there are probably 4 or 5 papers which address this problem specifically. So if you have that problem, come to me afterwards and I can point you to the stuff. I think there's a paper by Subin Garamani who addressed it, and I think we also have a couple of things that we did. So, very good question. So what this shows you is that the set of practical problems is vastly larger than the set of problems that I've discussed right now. And in many cases, solving a machine learning problem will, so in the easiest case, your problem fits exactly into one of those categories. You download a piece of software, you run it, and you're happy, and you move on. In quite a few cases, your problem will not be quite that straightforward. And then, if you're lucky, somebody will have already solved that, and you need to tweak something a little bit to solve the problem. Or in some cases, nobody will have solved it, then you solve the problem, you write the machine learning paper, and then you write the applications paper. Yep?
So can we really predict the stock market using machine learning techniques?
A lot of people claim to be doing this, and last time I checked at NIPS, there were at least 3 hedge funds eagerly trying to hire people. So machine learning must be to some extent useful. I think to some extent they are doing high frequency trading. I think there is more than just noise in the signal. That said, how much signal there really is, okay, I'm not sure. I mean, I think you'd have to work with a hedge fund to really find out. Yeah, basically ask somebody who's worked there. I wouldn't know. Yep.
I didn't quite get the difference between prediction and regression.
Okay, awesome question. So the difference between prediction and regression. Right. So in regression, well, let's say I give you a couple of, let's say I observe jointly the height and the weight of some people, right? And then I give you the weight of somebody, and your task is to tell me the height. So in that case, the order in which I observe those observations doesn't really matter, right? I could pick, half of the class at random and, record height and weight, and then I give you, the weight of somebody else, and you can guesstimate how tall they are. For prediction, that's not so cool, because if I already tell you, well, in October, the shares were at that value, then your task of, predicting that, of regressing, what the shares were mid-September is so much easier, right? Because you already know where you have to be in October. But prediction in this case means, predicting for the next day, predicting for tomorrow. So you have a time series. So the big difference is here, it's really a time series prediction model where you only know everything up to today, and you need to forecast what's going to happen in the future. And then you observe something, and then you move on, and you predict something for the next step, and so on and so on. So this is, you can try that with stock markets, you can try that with events. So there's some very nice work by Radinsky et al. So they took basically 100 years of New York Times and actually tried to figure out what are predictive precursors for some events. And so they found out that, floods and so on are pretty good predictors for cholera, for instance.
Can we categorize this prediction as a reinforcement learning, or?
I wouldn't treat it as reinforcement learning. So reinforcement learning is a lot more general, and we'll get to that a little bit later. Because, well, actually with the stock market it may very well be, actually for the stock market you might be right, because the market responds to what you're doing. So it won't respond to me, Alex, investing a few $1,000s on the stock market, but if I'm, let's say, JP Morgan, I don't know whether they're still in business, but assuming they are, and they invest, many billions, this will actually move the market. So there's a clear difference between, in this case, taking action to the extent where the environment responds, and taking actions and the environment has the same state tomorrow as it has today. Very nice application of that is economic policy in the United States versus Australia. Australia is small enough that no matter whatever Australia does, the world market doesn't really care. And so all the textbook economics works really well there. For the United States, it's a lot bigger, so it doesn't work so well anymore in this way. But yeah, it's a very good question. So this was actually a simplification that I made. Other questions? Okay, then let's move on to unsupervised learning. By the way, great that you're asking. I'm really happy with this. Okay, so unsupervised learning is a lot more fuzzy than supervised learning in the sense that it's quite often not even quite clear what the question should be. So let me give you a few questions you might ask. You might ask clustering. So that's find a set of prototypes that represent the data. Or you could ask, what are the principal components? So is there a subspace that neatly represents the data? Or, in sequence analysis, maybe can I segment the sequence? Or maybe are there some, underlying segment dynamics that explain it? Or maybe there's a continuous state. Or maybe there is a hierarchical representation of data. Maybe there are some independent components. Maybe there are some novel, unusual observations. And I'll go through all of this in a bit more detail. So let's have a look at this. So clustering, well, you could cluster documents. Say this is about sports, this is about politics, this is about movies, God knows whatever. You could, cluster users. Let's say there's a high spender, this guy doesn't have much money, the next one's a student, whatever. You could cluster web pages, you could cluster diseases. So for instance, this is a big deal when you want to treat cancer. So sometimes you have those cancers which look almost the same but have very different genetic markup. And depending on what went wrong genetically, you need to treat them very differently. And in the past, it used to be that somebody would have this cancer, and two patients would look exactly the same. You give them the same treatment, and one magically recovers, and in the other case, well, they don't. And that is quite often the case if the underlying causes are sufficiently different that you cannot just from the symptoms distinguish them. So it would be good if you could actually identify those subtypes. You can cluster pictures, vehicles, whatever. Mind you, clustering is not the only thing. There are a lot more refined things like topic models which will help you, but this is really just to give you the gist of it. Principal components, well, it's basically, try finding a subspace. Let's say observe the temperature and the pressure, and maybe there's some sort of nice linear relation. So it's enough pretty much if I know the temperature to infer what the pressure might be. You might, laugh at that, but actually, like in a paper from 2010, one of their key techniques, was principal component analysis to figure out some genetic variation. And so they found out that, hey, the principal components correlate quite well with longitude and latitude for some people in Lapland. Not quite sure why this is useful, but you could write a paper in Nature Genetics 2 years ago. So this is fairly high profile with a technique that's essentially a century old. Sequence analysis, well, you might want to discover some parts in it, again, another paper from Nature, and detect segments of coherent activity. You might want to figure out when the fridge is on or switched off on the computer or whatever goes on, based on the electric power consumption that you have. And again, you can't really invade people's houses and ask them, did you switch your fridge on? But what you can do is you can actually record those signals at the meter level, and so you'd hope that you can turn that into information. Some hierarchical groupings. So these guys, Adams, Garamani, and Jordan, took a data set of about, I think, 50,000 images, and hierarchically clustered it. And so this is zooming in further and further, and you can arguably see that at the leaf level, these are actually fairly nice and coherent images of whatever color. So does anybody have a guess what's up here? What's the most primordial image? Any guess?
Cats.
Well, no, that would have been a different algorithm. I think you read the New York Times. They had lawnmowers.
Okay.
So the divine image was a lawnmower, just because it probably looked like nothing else. But they had clustered lawnmowers. Independent components, So you might have heard of the cocktail party problem. You've probably experienced it at some point if you had a really bad cold. You got off a plane and one of your ears clogged up. Otherwise, just do the following thing. At some point when you're standing among a lot of people, shut one ear, try to follow the conversation, and you'll have a very difficult time doing so. Basically, what your brain is automatically doing is it's demixing the various signals. So you might have experienced that also when you're in a coffee shop and there are a lot of people talking. You can probably still study quite well. But if there's like this one person who really stands out and it's just really impossible to ignore, you really can't study, right? So it's basically your brain choosing to, or choosing not to demix things. And this is basically, you observe a bunch of signals, you have some sources, you want to then identify what the underlying root causes might have been. This is, for instance, really useful, well, for audio analysis, but it's also useful for, magnetoencephalogram. Basically, if we want to record brain activity and find out what's wrong with your brain, or just overall understand it. So there are a lot of really useful cases where this can be. Question?
Yeah, well, for the unsupervised learning, how can you really understand that? Like the clustering, finally you got all these clusters, how can you understand the meaning? The PC, you choose some features, how can you understand the feature without really looking at it?
Okay. So it's a very good question. Basically, with unsupervised learning, how do we know it's good? So first of all, we don't always know whether it's good. So this is the probably very frustrating answer. However, what you can do is you can define various measures of reconstruction. So for instance, you could say, well, if I were to generate data from those clusters or whatever, does it look like the real thing? So you can define some reconstruction error, for instance, how far is that vector from the original data? Or how well does it model the distribution of the data? So basically you might get the density estimate, and we'll cover densities on Wednesday. And then I can basically just ask, how likely would the observed data have been under that model? So I can use it to generate data, I can use it to reconstruct things, I can use it in some cases, for instance, to find unusual events. So novelty detection, we'll get to that on the next slide. So that's why it's actually quite important for a lot of those algorithms to start out with at least an objective function that is moderately undisputed. That's not always entirely possible, but usually for a specific application domain, people will have some idea of what it means to reconstruct the data. So for instance, if I do some analysis on images, then it's very easy for humans to just look at those images and say, well, that looks like garbage, or that actually looks like a human or a cat, for that matter. You might have similar things for activity logs, and you might, for instance, want, in this case, to be able to then, generate similar activity logs as what you've observed. So that's one of the main difficulties of unsupervised learning, that quite often the first thing that you actually have to do is to establish what it means to understand the data. In some cases, it may simply mean, well, find me the most frequent items, or find me the really unusual items. And as soon as you've defined that question, the rest of the algorithmic design is a lot easier. But that very first part is, probably the hardest and the most fun part of the problem. Oh, very good question. Any other questions? Okay, so we have novelty detection. Given that we're running a little bit behind schedule, I'm not going to have a break. Is everybody okay, or otherwise just, do whatever you have to do by running out and coming back? Novelty detection. So here are some images of, in this case, houses or, faces. And what you want to be able to do is you want to detect both the really typical ones and the really atypical ones, and we'll actually encounter a couple of algorithms which will do that very thing for you. So now, besides the supervised versus unsupervised, in many cases the data arrives at you in interesting forms. So the simplest case is that, so the first abbreviation you need to remember is IID. Independently, identically distributed, it basically means life's good. Whenever you see IID, you mean things are fine. In many cases you can approximate this way, but in reality quite often it won't. So the standard induction setting is basically, you have to get some training data. Let's say you get some handwritten digits and the numbers that go with it, and then you afterwards deploy the system, let's say in a postal office, and there you need to do well. For new images, you need to be able to, say whether it's a 1 or a 0 or whatever. So in other words, the test data is not available at training time. Transduction, this is basically having the test data available at training time. So that would be a little bit like, let's say, me giving you the exam questions already beforehand, so then you would be able to study really, really well to be able to answer the exam questions, right? So in other words, you're not really building a system to answer arbitrary questions, but just those specific exam questions. Then there's also what you can call semi-supervised learning, and in that case you basically have the labeled data, and then you have a lot of additional unlabeled data. That would be like me having been here for a few decades and you looking at all my past machine learning classes, looking at the exams that were handed out at the time, and inferring from that, okay, he might be asking such and such a thing. Right. Covariance shift is when your training and test distribution aren't quite the same. So imagine the situation where maybe I set up the problems for the homework, and the TA set the questions for the exams, and you've probably had cases in the past where the homework and the exams are very different and you were very frustrated. Right? And that's covariance shift, because you've basically trained to solve the homework really well, but then the exam is quite different, and so you can easily see that thing may fail quite a bit. Code training, that would be basically observing a number of similar problems at once, and let's go into a bit of detail. So this is a data set. It's called the 2 half-moons problems. By the way, never publish a paper on that. That's pretty much the easiest rejection criterion for a paper. But it was basically a simple toy example to illustrate things where people then afterwards actually used it to argue that the algorithm is correct. But it's a different story. Basically, you have one point here that's blue, another point here that's red. And it's quite reasonable to assume that this all should be red and this all should be blue, which is what you get here. And so an algorithm that doesn't have all those black unlabeled points would probably put the linear classifier or some sort of separation in here and give you that answer. Whereas if I do transduction, basically get all the other points, I'll probably get this right. So that's the difference between induction and transduction. For covariance shift, so this is unfortunately a true story. Some biotech startup that I worked with, they wanted to detect prostate cancer, and they had to figure out that some markers in the blood were really useful to figure out whether their patients had prostate cancer. But for various ethics and clearance reasons, it was really hard to get blood samples from healthy patients. It sounds kind of bizarre, but okay, that's what it is. So what they did, and this was incredibly stupid, it was cost them, probably the equivalent of a luxury car. They went out, because they were on a university campus, and got a lot of blood samples from male university students. And then they used that as a reference, they ran their analysis on it, and they said, hey Alex, can you, now use that, we have positive, negative classes, can you, detect cancer? Well, and I say, well, hey, yeah, sure, I'll build your classifier, they can see perfectly right. It's going to be perfectly useless. Does anybody have an idea why this would have been useless? Exactly. Age, alcohol consumption, physical activity, lots of other things, hormones. So In other words, it would have basically built a young people detector. Yeah. Because I mean, it's old men usually who get prostate cancer.
What do you mean 100% accuracy?
Well, it would have perfectly well if, you know, the distribution of data that you would have gotten out afterwards would have been drawn from the same distribution. In other words, you know, old men with prostate cancer versus, you know, young university students, you would have almost certainly gotten that distinction perfectly right. However, if I were to deploy this at a doctor's office where they, you know, go and take a blood test, and you have some patients where it's kind of questionable, maybe they have prostate cancer, maybe they don't. So these would all be men in their 40s or older. It might not have worked very well. There are a couple of other examples of that form. So as a puzzle, the US Army at some point wanted to detect whether there are tanks hidden in a forest. So what they did is they flew over that forest and took pictures, then they drove the tanks in, they flew over the forest, took some more pictures, they built a neural network and it worked perfectly. Why was it completely useless? Think about it. Yep.
There were clouds in all the original tank pictures, and no clouds in all the non-tank pictures.
I haven't heard that part of the story, but I heard that basically the shadow went in the wrong way. Basically, they took pictures in the early morning and then at noon. But yes, you're exactly on the right track. So just to speed things up a little bit, code training and multitask. So multitask is basically you have a whole bunch of different tasks. You, let's say for a web page, want to detect whether it's spam, whether it's person's homepage, or whether it's adult content. And usually those things are reasonably exclusive from each other. For code training, well, you might want to detect, you know, whether it's a spammy web page based on the page content, another one, you know, based on, you know, whether users actually view it. And so you have basically twice the same task, but based on different data sources. And in both cases, you can do better if you solve them all jointly. Now, this is really important interaction with the environment. Batch, this is basically like you download a book and you just observe the training data, then you build a model, you deploy. For online, this is like you follow the class, well, you listen to me and Barnabash every week, and then you improve your model of what machine learning is, and you get better and better at doing homework, or same thing for the stock market. Active learning, you can actually ask questions, and you can basically say, well, you know, if it's such and such, well, what should it be? And you can use that to improve your model. Sometimes it's really faster. Bandits, well, you basically take a decision, you get the reward, then you update your decision and you do that. Reinforcement learning, well, the environment actually responds. So a few pictures, batches, basically, you know, you get some data set like for Netflix, you run your algorithm, you build a model, and then you deploy it. Online, you get, you know, data label pairs. Each step, you update, you update, you update. And it's, well, let's say you know, choose an option, you see what happens, because the only thing that you're going to see is for whichever bandit you pull the arm, and then you move on. Now that sounds awfully contrived, but if you, for instance, have a web page, you're operating a web page and you have different layouts, different content that you could show for a given user, you only get to see the response for the action that you took, not for all the actions that you could have taken. Reinforcement learning, basically the environment will actually respond. So I assumed before that for the bandits, the user essentially has to mimic the goldfish. But in general, for an environment, I mean, it might actually cooperate with you. It might be adversary, like in the case of playing chess, or it might not really care either way. It might have a very long history in terms of what the state that remembers. The state space itself might be very simple or complicated. You might not be able to observe all of it. So all those things play in reinforcement learning. So in a way, reinforcement learning is the most general of all of those settings. But the specific settings, the narrow ones, are sufficiently useful that it actually pays off designing the algorithms for it. Discriminative versus generative. So this mainly matters for, you know, supervised models. So discriminative, you basically want to estimate y given x directly. And for generative ones, you jointly estimate x and y, and then you get p of y. So let me show you an example. For the distributive model, if I have those two distributions of, red and green dots, it doesn't really matter very much. So I get the same model, and I'll be giving you the same answer. In a generative case, well, those two might actually lead to very different density models for, the red and the green bits, and then they might lead to a slightly different decision boundary. And we'll get into that in a lot more detail. Now, I'm going to walk you very briefly through some of the more basic tools, and we'll pick up on that again next Wednesday. Wednesday in a week, because next Monday is a holiday. So, nearest neighbors. So the simplest thing that you can do is, you can just do a simple table lookup. So for instance, you could just, this was exactly the question with the helicopters. Well, can't I just, remember all the control actions and then replay them? And, well, if we don't quite do that, but something very close, then we'll basically, just pick the label or the action or the regression value of the most similar neighbor. And the slight improvement would be, well, we don't only take the nearest guy, right, but we take, the majority of the nearest 3 and nearest 5 or whatever. And this is really, really easy to implement for small amounts of data. So by the way, why is it really easy to implement on small amounts of data?
Because you don't have to measure that many pairwise distances.
Correct. Correct. And for large amounts of data, this is essentially hopeless, and you need some fancy data structure. So for instance, core sets might help you. So here's what happens if I have something that's actually, I just took two Gaussians, had them slightly overlap, and so that's okay with the colors. If I take the nearest neighbor classifier, these are all the regions that will be classified as red, and these are classified as blue. So you can see this tessellation, and you can see that this is actually quite awful around here. If I take the 4 nearest neighbors and I color coded, where I have 4, 3, 2, or 1 red one, and then, likewise the blue ones in majority, and I look at the corresponding decision boundary, you can see that this one looks a lot better. So, actually, this is something for you to think about why this is the case for one nearest neighbor. If we get more and more data, well, if there's a perfect separation, it will converge to, the perfect solution. But if the problem is noisy, then, well, we'll basically get twice that minimal error rate for noisy problems. You can work out for yourself why we get twice that rate. And for k-nearest neighbors, well, again, we get the perfect solution, but we need a bit more data, and we get that minimal error rate if k increases. So, in other words, we actually need to look at larger and larger neighborhoods as we get more data. You can work that out for yourself, how to do this. But we'll pick it up again next week. Here's a very simple tool, and yeah, okay, I guess we're basically out of time, but we'll pick it up again on Wednesday. So linear regression. So, well, what's linear regression? Well, I have some function f of x is ax plus b. So remember Ohm's law, right? He just actually removed that constant offset. So, some linear dependency. So if I want to, find some parameters a and b that fit the data really well, so what I can do is I can just minimize with respect to a and b, let's say the squared distance between what I estimate and what I observe. So, I have this objective, I take the second derivative and I get those two equations. And if you squint hard enough at it, you can see that these are linear equations in a and b, and you can solve them. Actually, let's write it in such a way that you don't have to squint. So let's rewrite the optimization problem f of x as f of x is a dot x plus b. Right? This is w dot, now the vector of x and y. So I've just, stacked the constant onto the vector of x. So we're actually doing the vectorial case here. Okay. So now the optimization problem is this. So it's exactly the same as what we had before. Then you take the derivative with respect to w, and you get the c. That's why I have the 1/2 here, such that the derivative makes, look nice. And so then by pulling out terms, you can rewrite it as such. Okay. And now if I want to solve for w, which is what I'm really after, I just need to invert this matrix, multiply it here on the left-hand side, and w just comes out. Anybody has a question at this so far? So this is really just minimizing, the square distance. Okay. Now what do we do if we have a nonlinear problem? Well, we can actually do the same trick, right? So rather than, taking 1 in x and treating it as a two-dimensional vector, we could take 1 in x and x squared, 1 in x and x squared, and x to the 3, or more generally, just some function phi of x, which is, just some vector. And so what you're going to learn now is how to do nonlinear regression. So remember, linear regression had that problem, right? Now nonlinear regression looks exactly the same. Compare it, right? So the only thing is that where we had x bar before, we now have phi of x. So we minimize w dot phi of xi. And now solving it means that we have to compute this outer product matrix. We invert it and multiply it in the left. That's the only real difference. Everything else is exactly the same. So here's the pseudocode for degree 4 polynomials. So here's your first machine learning algorithm that you can use. 2 lines. You compute the features. You then compute the vector. So this is multiplying by the inverse of the vector. All in octave. It's a symmetric matrix, so this is fine. And then here it is. Let me show you what happens in practice. This is for a linear function, and well, the blue thing is the actual function that I wanted to get. The stars are basically samples from that function with some Gaussian noise added. And now let's see what happens if I take a quadratic function. Lo and behold, it actually does a pretty good job at fitting a quadratic function. Right? They're basically taking those blue dots and regressing, and lo and behold, I get something that looks not too awful. If I have 3 dimensions, it's actually still sort of okay. It fits the individual points a little bit better, but the overall fit is worse over here. For 4 dimensions, you can hardly see a difference. If you squint, you'll see something move a little bit up there. There's no difference. But now things go badly wrong, right? Wow. Completely shoots up here, breaks down there. 6 dimensions, it gets worse. 7 dimensions, it gets even worse. 8, oh my god, 9, complete disaster. And if you actually run this, this is what Octave will spit out. It basically says, well, matrix singular to machine precision, and everything is really bad. So why does it fail? And the reason why it fails is because we basically try to infer too many parameters, have a really underdetermined model, given the data. The data was quite noisy, we didn't really take that into account. In other words, our first primitive machine learning algorithm was way too primitive to really do anything useful. So there are, in a way, 2 things that can go wrong. One is underfitting. So that basically was the case where we tried to fit a linear function on, the quadratic data coming from a quadratic function. And that can go wrong. The other thing is overfitting can go wrong, where I basically have a function that's way too complicated. And I don't have enough data to really infer all those parameters, and then something can be quite horrible. Now, how to adjust those parameters to pick the right model, to deal with all those various idiosyncrasies, these are things that we will be going through in this class. So I hope that at the end of the class, you won't really get this anymore. Or at least you'll understand why it fails. Okay? Okay. Okay, so this is the end of the class. If you have any more questions, by all means ask or post them.
Will the slides post online?